And so the last bit on our muscles, our part C, looking at different types of muscles and muscle tissues, and not just skeletal muscle, but still continuing with our conversation on muscle contraction. In this part, we're going to be looking at the force of the muscle contraction, not just the fact it shortens or lengthens or the fact that you can generate tension. We're looking now at the force of your muscle contraction. Now, the force of our muscle contraction is dependent on the number of cross bridges that are attached. These are the myosin heads attached to the actin. So it's how many of those myosin heads can attach to actin. Now, that is dependent on four basic things: the number of muscle fibers that are stimulated or recruited, the size of the fibers, whether you have really large cells or not, the frequency of stimulation, and the degree of how stretched out your muscles are. So this is looking at kind of those four basic ideas. The number one, as more muscle fibers are recruited, and I'm like, as more are stimulated, you're going to generate more force. Kind of makes sense. The more, if you bring in backups, if you recruit more people, you can generate more force with more of you working together. Same, another kind of basic idea is the size of the fibers. Bulkier muscles, meaning the cells are enlarged, called hypertrophy, you can generate more force. Also, when you think about it, and make me lifting some weights and a big old muscle builder guy lifting weights, they're going to have way bulkier muscles than mine, which is fine, but they can also generate a lot more force. Also, we're looking at the frequency of the stimulation. If you increase the frequency, the time for transfer of tension to non-components, is going to decrease, and so you can generate more force. You don't allow the muscles to relax in between hand, and you can generate more force. Also, it looks at the stretch of the muscle. It's this length-tension relationship. Muscle fibers that are somewhere between 80 to 100% normal resting length, meaning they're just kind of at resting length. They might be a little bit shorter, might be a tad bit stretched, but they're at normal resting length. You can generate more force. When you think about it, if you've got just your bicep brachii, that arm muscle, and if it is nice and stretched out, just long, your whole muscle's long, you can generate a lot of force and you can lift weights using that muscle. If your muscle is already contracted, if it's already shortened, you can't generate a lot of muscle if it's already been shortened. Same thing if you've overstretched it. If you're someone that can overstretch your arm muscles, hyperextend them, you can't generate a force if it's overstretched. So you can generate the most force if it's just kind of at your normal resting length. This again is just kind of looking at those four basic ideas: is the number of muscle fibers recruited, the larger the muscle fibers, how much stimulation, what's the frequency of stimulation, and if you're right around 100%, maybe slightly stretched or slightly lower, you can generate the most force in your cross bridges. The most myosin heads can attach to actin. This is looking at that length. If your sarcomere is at your normal resting length, it's just, your muscle is laid out. It's not contracting, it's not stretched. It's at normal resting length. And you can generate the most force right here at 100%, maybe a little bit less, maybe a little bit more. But if it's already shortened, the myosin heads can't attach as many places. And if it's already stretched out, this myosin head can't reach all of that actin to attach there. Other things then, the force that can control contraction is the velocity and the duration of your muscle contraction. The velocity, so how fast can your muscle contract and how long your muscle can contract, are influenced by three things: the muscle fiber type, your load, and the recruitment of the muscle fibers. Now, muscle fiber types are put into two different groups. They're not really two groups, three different groups, but they're based on how fast they can contract and where they get their ATP from. So, and there's going to be kind of three basic different types of muscle fibers. Now, speed of contraction, slow or fast. That's as extensive as we get. Do they contract slow or do they contract fast? This again is how fast we can split ATPs up and how fast we can use their energy and how fast that electrical information can travel. The other part that tells us what our characteristic of our muscle is where we get the ATP from. Is it oxidative, meaning we use that aerobic pathway, part of oxygen, or does it use anaerobic glycolysis, that breaking down sugar into pyruvic acid, which eventually can get into lactic acid, through glycolysis. We call them glycolytic fibers. And so whether it's using oxygen or not using oxygen, you can still generate different types of ATP. So by mixing the words slow or fast, and whether it's oxidative or glycolytic, we have three basic types of fibers that we find in the human body: slow oxidative, fast oxidative, and fast glycolytic. Now, some information on each of the three. Slow oxidative fibers. They're called slow because they contract slow, but they're also slow to fatigue, so you can contract them for longer periods of time. The oxidative part means that it does need oxygen, so it needs lots and lots of oxygen in an aerobic process to make all of its ATP. In these fibers, we also have lots of mitochondria to make all those ATP. There's also a pigment in these muscles called myoglobin. Again, anything with myo means muscle. It's called myoglobin. It's an oxygen-binding pigment found in muscles. It may sound something similar to hemoglobin, which also binds oxygen, but in red blood cells. This is myoglobin that binds oxygen in muscle cells. Now, having lots and lots of myoglobin makes these particular muscles actually have a nice red appearance to them. So we've got lots, and because of that, because they also need lots of oxygen for their process, they also have a lot of blood supply. So lots of blood there, lots of myoglobin making it appear red, lots of mitochondria, contract slow, but it also can go for long periods of time. Now, I'm going to flip around. I'm going to come back to fast oxidative. Fast glycolytic. We're kind of going on the opposite end. Fast glycolytic. Fast means it can contract fast, but it also tires fast or fatigues fast. It doesn't use any oxygen because it makes its ATP through glycolysis, which is an anaerobic pathway. It also, because it doesn't need the mitochondria, because we use that when we make ATP with oxygen, it doesn't have very many mitochondria in these types of muscles. They also have very little myoglobin. Again, myoglobin is an oxygen-binding pigment. Well, these make their ATP not using oxygen, so very little myoglobin. So these muscles actually appear very light colored or white. And I'm like, so you kind of have your basic red, lots of oxygen-binding pigments, white, very few oxygen-binding pigment. Fast oxidative is kind of right there in the middle. It kind of has some intermediate characteristic. Yes, it can contract quickly, and I'm like, but it also uses oxygen. I'm like, so it still has lots of myoglobin because it still needs to hold lots and lots of oxygen, but it's kind of right there in the middle, the kind of intermediate characteristics. Now, because it does have lots of myoglobin, not as many as slow oxidative, so they usually say this kind of appears pink in the middle. Now, most of the muscles in our body have some type of mix of these fibers. It's rare to have only one of them, and this can help, change our contraction speed and how fast we tire. Now, all the fibers in one motor unit are the same. So that's one motor neuron, and all the fibers that it controls. It would control, that one motor neuron would control all slow oxidative or all fast oxidative or all fast glycolytic. And your genetics dictate the percentage you have of each of these muscles, these muscle fibers in your muscles. So I myself, genetically, I am not born to be an Olympic sprinter. However, there are others, and yes, Olympic sprinters can have kids that are also born with really fast glycolytic fibers, and they can do those sprints. I'm not one of them, but that's based on genetics. And I'm like, most of us have kind of a nice mix of both, where you don't have one or the other in an abundance. Now, this again is kind of just comparing your slow oxidative, fast oxidative, and fast glycolytic. This was just showing those colors. Your slow oxidative are more red in color, your fast glycolytics are pale or white in color, and your fast oxidative is kind of in the middle. Now, this, if you ever wondered about it, if you say, head to KFC, and they're like, do you like white meat or dark meat? Guess what it's referring to? It is referring to white meat is generally, that's your fast glycolytic fibers. The muscles where you find white meat are made to do some type of contraction, but for short amounts of time. And a chicken, that would be the wings. They're not made to fly large distances. And so we would have white meat there. Dark meat, this is where it contracts slow, but it can go for long periods of time. That would be the legs. Chickens can walk around all day long just fine. So they have lots of those myoglobin pigment to make sure they've got lots of types of oxygen. So, makes you think twice a little bit on next time you order white meat or dark meat. There's a reason for the white and the dark. It's just how much myoglobin is there, depending on how much oxygen is needed. Now, the influence of load on muscle contraction. I like to think this kind of makes sense. Muscles contract faster when no load is added. I can contract my arm muscle a whole lot faster if I'm not lifting anything versus I lift 50 pounds. And I'm like, so if there's no load, if there's nothing I have to push, I can contract a lot faster. Once you start increasing that load, yes, the latent period, how long it takes to activate all those fibers, it takes longer. Your muscles are going to contract slower, and you're not going to be able to contract for as long either. So it kind of makes sense. This is just showing different sizes of load. The lightest load, you're going to be able to contract for longer periods of time. The heaviest loads, it's going to take longer to start contracting, and it's going to take a lot longer. This is looking at speed. The heavier it is, the slower it is to contract. Then we're looking at influence of recruitment. Also kind of makes sense. And I'm like, this is recruiting of motor units. And I'm like, the more you recruit, the more motor units you recruit, the faster the contraction, and you can increase how long you can contract. Again, makes sense. The more people working on a project, the faster that project gets done. So the more motor units you recruit, the faster they work together to make the contraction happen. So these things all help influence contractions. Now, if you're wondering, well, how does exercise help? So if you start an exercise program, what does that actually do to your muscles? One, if you're working on aerobic or endurance type exercises, you're like, I'm going to run my first couch to 5K. Well, every time you go out and run, that leads to more muscle capillaries. We can start bringing more oxygenated blood to your muscles. The number of mitochondria are going to start to increase. The number of mitochondria can change all the time depending on the needs of your muscles and the needs of your cells. If your muscles realize they need to make more ATP, they're going to have more mitochondria. You're also going to have more myoglobin synthesis so that we have more of those oxygen binding pigments to hold the oxygen. This, every time you go out and run, results in greater endurance, more strength, and resistance to fatigue. So one day you can run 3 blocks, the next day you can run 4 blocks, the next day you can run 5 blocks, because each day you're going to increase the number of capillaries and mitochondria, and it takes longer to fatigue. Now, what's also can happen is that it may convert some of your fast glycolytic fibers into fast oxidative fibers. It does not change them into slow. It can just change how they make their ATP. And I'm like, so there's still a fast twitching fiber, so it can still contract fast. However, it can now contract fast, and because it can go from glycolytic to oxidative, I'm like, it can make more ATP by doing it this way. Now, if you're instead, you'd rather decide to, I don't want to run a marathon, I'd rather like to bulk up a little bit, then you have your resistance types of exercise. This is your basic weightlifting. Now, this is your typical anaerobic, is you're trying to, work those muscles, they will start to bulge. Now, the number of muscle fibers themselves do not change, and I'm like, because you're born with whatever muscles you have. However, the size of your muscle fibers can change because you start getting more myofibrils. You still get more mitochondria. They still need oxygen. They still need, they don't need oxygen. They still need ATP, which, yes, using oxygen can help. We're going to get more myofilaments because you're going to need more actin. You're going to need more myosin and all those myofibrils. You're going to have increased of glycogen stores, so those muscles have quick energy right there and more connective tissue. It will also then lead to increased muscle strength and size, hence the picture the size. Yes, that guy is going to lift way more than I would be able to lift. Now, the little note that I had as well, that they're saying that just a few minutes of basic weightlifting every other day can add 50% more muscle onto your body. over a year. So just doing little bits of muscle training is going to increase the size of your muscles. Now, usually when you're doing this, doesn't matter whether you're doing the trying to lift weights to bulk up or you're trying to train for some type of aerobic. Both ways, you're still doing what's known as the overload principle. You're trying to force your muscles to work harder than they would like to. By doing that, you're pushing them, and then those muscles are going to start to now adapt to those increased demands. They're going to start to get those more mitochondria. They may start to get some more myoglobin. And so they're going to start to produce gains once they're overloaded. Now, the times people start injuring themselves, because everyone's like, oh, well, I have to work myself beyond what I normally should. That's usually when you get to what we call overuse injuries, that you didn't let your muscles recover. It takes a little bit for your muscles to adjust to that overload, adjust, compensate, make them more mitochondria, increase what you need before you start using them. And so while it's building, if you now overuse it again, that's when you start to get injuries. So the best exercise programs alternate aerobic with anaerobic. It's you build muscles, but then now you're just, you're using them in a different way, aerobically, and kind of going back and forth to build them up. And the opposite then, instead of trying to build any muscles, is what happens if you don't use them at all. It's called disuse atrophy. Again, anything with the A means without, and it just means, the whole word means without nourishment. And I'm like, if you don't use them, if you don't use your muscles, you lose your muscles. Now, usually you use your muscles in some capacity, and I'm like, even if you're walking, we're talking about, complete immobilization. And I'm like, if you've got certain muscles that are in, or certain parts of your body that are in casts, or if you're in a wheelchair for a long time, or if you're in on bed rest, your muscle strength can start to decline 5% per day if you're not using it at all. And we're talking at all, like in a cast, physically can't move it. Now, and that's why I'm like, if anyone's ever had a cast off, and all of a sudden, off a leg or an arm, and you looked and you could see the difference in your two body, whether the two arms or the two legs, you can see the difference in what happened when you didn't use them. Now, if you have no neurostimulation to your muscles, they will actually atrophy to about a quarter of their size. This can happen for people that have damage to their spinal cord, where there's absolutely no neurostimulation to their muscles whatsoever. Those muscles start to go away. They're not needed. Now, what can happen when you're not using those muscles, there's no neurostimulation, any of that connective tissue that was found in your muscles, or any of the muscle tissue itself gets replaced with a fibrous connective tissue. It's almost like a scar tissue. And so for people who have had some type of damage to their spinal cord, they're now in a wheelchair, and all of a sudden 10 years later they're like, we have this new technology, and I'm like, we can make you walk again. They can't, because those muscles, haven't been used in so long that the muscle tissue turned more into a connective tissue, or this scar tissue, and you can't regenerate it back again. And so that's when rehabilitation becomes impossible. So it really is, they have to get back into physical therapy right away if there's any damage to muscles, to make sure that they don't atrophy. Now, since we've been talking lots and lots about skeletal muscle, yes, this unit is about muscles in general, and so there are other types of muscles, like smooth muscle. Places we find smooth muscle, we find it in the walls of most hollow organs, meaning stuff's going through it. And I'm like, exception is the heart, because that's its own separate muscle. Also, if we looked at it, here's an example of the intestine. It's a hollow organ because stuff's going through it. And I'm like, it's double layered. Now, there's a longitudinal layer and there's a circular layer. Longitudinal meaning it goes lengthwise. So it would go lengthwise with the actual organ. Circular just means it goes completely around in a circle. Now, these two muscles will work together to help muscle contraction. So I'm like having the two different types of muscles. Now, if we zoomed in on smooth muscle, yes, some of the biggest things that we can tell about smooth muscle, there are no striations. There's no stripes, hence it's smooth. It only has one nucleus. It's thin and short compared to skeletal muscle fiber. Because skeletal muscle fibers, they can run for, inches, if not feet long. These are tiny, stretched out little kind of football-shaped things. They lack those connective tissue sheaths. They don't have an epimysium and a perimysium, and an endomysium. They just have endomysium only. That's it. That's all they got. Also, they do have a sarcoplasmic reticulum. Still has calcium. Not as developed as in skeletal muscle. They don't have it where it forms these triads and everything else. Also, there's no sarcomeres, there's no myofibrils, and there are no T-tubules. They don't contract in the exact same way, and they're not as organized when they contract as skeletal muscles do. Now, kind of back to my longitudinal layer and circular layer. The longitudinal, again, goes lengthwise with the organ, and so it's parallel to the long axis of an organ. Goes lengthwise with it. When it contracts, it dilates and shortens. So when it contracts, it actually gets wider, and the whole muscle contracts. So widens and shortens. The circular layer, this inside layer that goes around that cavity, so it's the circumference of the organ, when it contracts, it constricts or makes this opening in the middle smaller, which then again stretches or elongates the organ. Now, because one dilates and shortens and the other one constricts and elongates, they do opposite of each other. And so our organs, all of these hollow organs, whether it's your intestines, whether it's your blood vessels, and I'm like, whether it's your urethra, your ureters, any of these different types of things, because we've got these two layers doing opposites, we can alternate the contractions, and it allows us to squeeze things through this opening in the middle, whether it's squeezing food through by squishing and stretching and lengthening, and I'm like, or it's pushing blood through, or it's pushing urine through. Just by having these alternating back and forth, it allows things to kind of squeeze things through the lumen. This alternating contraction, squeezing things through and moving them along, is called peristalsis. It's, just kind of squishing things through. Now, this is just a nice little summary. It's in your book, and I'm like comparing it. Your book, it's page 310, and I'm like, it's got the three different types of muscles. However, we're looking at the smooth, so they have one single nucleus, and I'm like, they're all attached. I'm like, no striations. They're all kind of hanging out by themselves. And I'm like, they only have the endomysium. They don't have the perimysium and the epimysium and everything else. So, a lot more simple. Also, they still have to contract with some type of nervous system. The nervous system has some control over the smooth muscles. It's, however, controlled by your autonomic nerve fibers, aka they control it. We don't physically have any control of it. They happen automatically, and they attach at various junctions, and you usually have these bulbous swellings of nerve fibers. They're called varicosities, these little bulb-like structures called varicosities. It's in these where, if we zoomed in on one, yes, we've got various neurotransmitters that will tell the muscle to contract. And I'm like, kind of similar, like the end of an axon terminal. And I'm like, also has some neurotransmitters in it. And I'm like, instead of just being the end of an axon, we have all these little bulbs everywhere. They still are going to release their neurotransmitters into a small little junction found all around the smooth muscle. Also, a difference ratio of thick to thin filaments. This is your myosin to actin. And I'm like, we have way more actin to myosin in a smooth muscle. In your skeletal muscle, you had 2 actins to 1 myosin, and then it creeped along. And I'm like, in this we have way more actin compared to myosin. These thick filaments have heads along their entire length. Instead of just having just around a few places, they have them everywhere. There is no troponin, and they have instead a protein called calmodulin that binds the calcium. Because in skeletal muscle, troponin bound it, moved to the tropomyosin. Instead, our smooth muscle, this calmodulin binds the calcium. Now, these myofilaments, your actin and myosin, instead of just being straight back and forth in these repeated in sarcomeres, they actually spirally twist around. So if this is one big cell, we took these and twisted around and twisted around and twisted around. I'm like just twisting these around in one direction and then in another direction. So when they contract, they actually contract and almost form a little corkscrew manner that they end up squeezing the muscle together by having those kind of corkscrew arranged myosin and actin. Now, some other special features about smooth muscle. One is the stress relaxation response. The muscle, smooth muscle, can respond to stretch, even if it's briefly, and then adapt to its new length. It can stretch and then be like, all right. It still retains its ability to contract. Biggest examples of this is your stomach and your bladder. You eat something, your stomach's like, all right, I'm stretching, and then I'm okay with it. Adapts to its new length. Your bladder does that as well. As it starts to fill with urine, it stretches, and then it just adapts to that it stretches. Doesn't mean it can't contract. It still can, but it's just stretching. Now, the length and tension changes. This just means it can contract between half and twice its normal resting length. So it can get really small, and it can get really big, and still contract just fine. And I'm like, skeletal muscle, if you remember, it contracted best when it was right around just straight 100%. Tweak a little bit this. Not with the smooth muscle. It can stretch really big and still be able to contract. This happens maybe after, your Christmas dinner, your Easter dinner, where you just fill your stomach up so much that it hurts. That might be more than twice its normal size. And I'm like, doesn't mean it still can't contract. It can still contract. Also, smooth muscles can do what's known as hyperplasia. They can divide and increase in number. So we can actually have more. Skeletal muscles, numbers stay the same. Smooth muscles, they can increase in numbers. An example of when this happens for smooth muscles is your uterus at puberty actually enlarges. It gets more muscle cells. It has more smooth muscle. Also happens during pregnancy. Those muscle cells are not just getting larger. You're getting more muscle cells during pregnancy. So that uterus gets enlarged quite a bit. There are more cells there. Now, some developmental aspects. All skeletal muscle, or not all skeletal, but all muscle tissue in itself develops from what are known as myoblasts. If you remember osteoblasts, blast means build, myo means muscle. These are building cells. Now, cardiac and skeletal muscle become amitotic after they're made, which means they do not undergo mitosis. They can still lengthen, they can thicken, but you don't get more cells. Whatever cells you were born with your cardiac and skeletal muscles, that's what you've got. Now, then I'm like, the myoblast-like skeletal muscle cells have some regenerative ability. And so if you do damage some of your skeletal muscle cells, we have these building-like, they're not the exact same as the original myoblast, but they're myoblast-like. That gives you some healing ability. Now, this is kind of the same thing. We have some, they're called cardiomyocytes. These, again, are they're cells of heart muscle cells. They can divide at a rate, but injured heart muscle is usually replaced by connective tissue. So if you damage your heart, an example is a heart attack. It didn't get enough oxygen, muscle cells died because they need oxygen for the cells. Instead of replacing it with brand new cardiac muscle cell and having like a whole brand new heart, most of that damaged tissue turns into connective tissue or a scar tissue. So damage to your heart is a permanent damage. Smooth muscle, unique all in itself. It can regenerate throughout an entire life. I'm like, which is fine, because if you get poked with a needle, your blood vessels are made up of smooth muscle. That means you can heal. That blood vessel will heal just fine, and it can keep regenerating with any type of damage to it. Some other developmental aspects are kind of our development. Our muscular development reflects our neuromuscular coordination. So how our muscles develop depend on our nervous system. All muscle development occurs head to toe, so top to bottom, and from proximal to distant. So like we can control muscles close to the body versus the extremities. An example of this, and I'm like, for head to toe, I'm like, babies can control their head. They can hold their head up relatively early, within a few weeks after birth. But they are not walking around. They don't have control over the lower part of their body until a year later. And so I'm like, it's going from head to toe. Now, and I'm like, the peak natural neural control occurs by mid-adolescence, teenage years. And I'm like, so as a kid, you don't always have full control of your muscles. Maybe you feel like you run around like you've got two left feet and you're tripping over yourself. Teenage-ish years, whether it's early or late, you should be able to start controlling those muscles. And any time of athletics and training always helps improve any of that neuromuscular control. Comparing between males and females, female muscular or skeletal muscle makes up about 36% of body mass. Males makes up about 40% of body mass. just because testosterone is a hormone that increases the myofibrils and muscle contraction. However, body strength per unit of muscle mass is the same. If if a male has 5 pounds of muscle and a female has 5 pounds of muscle, and I'm like, each of those 5 pounds of muscle is going to be able to contract and have the same force. It's just males have more body mass made up of muscle tissue. And then, the whole aging sucks, that yes, as we get older, connective tissue, the scar tissue, increases as our muscle fibers decrease. And so we start to lose muscle cells, muscle fibers, and replace them with scar tissue. By the time you hit age 30, the loss of your muscle tissue starts to begin. The good news, regular exercise reverses this. You can build some of that muscle tissue right back up. So it's not a permanent, only doom and gloom. So, you start to lose muscle, but we can build it back up. You just do some types of regular exercise. All right, on to my last review questions. Sprinters typically possess more of these type of muscle fibers. I was going to say, well, it depends on how much training they have. Generally, you're going to have your fast glycolytic and fast oxidative. Now, and I'm like, again, it depends on your training and what you started with. Either way, they're going to contract. But if you have fast glycolytic in lots of training, you may start to get some more fast oxidative as well. What type of exercise can convert fast oxidative to fast glycolytic? Which I kind of just talk about anyways. I'm like, I was going to say, yes, sprinting, but I don't have it as my option. And I'm like, resistance exercises, lifting weights. And I'm like, can convert some of your fast oxidative to fast glycolytic. They don't need the oxygen, so we can go from oxidative to glycolytic. Injured cardiac muscle is repaired mostly as your scar tissue, as your connective tissue. And that was the end of this PowerPoint. So email me if you have any questions at all.